episode 142, Patrick and Cyprian speak with Huang, CEO of Quantum Computing Incorporated. The team discuss photonics as the bridge between quantum computing and communications, building hardware around physics, and cutting AI energy consumption with NeuraWave. Welcome to Entangled Things, your quantum computing podcast, hosted by Patrick and Cyprian.
Hey, Cyprian, how you doing today?
Hey, Patrick, I'm doing good. Looking forward for another great episode of Entangled Things.
I don't know how it happens, but our guests keep getting better. So today we're joined by Yuping. Yuping, can you please introduce yourself to our audience?
Hey, Patrick and Cyprian, and hey, everybody. Huang here. I'm the CEO and the chairman of Quantum Computing Inc., a public company. But I'm really also a physics professor, so very glad to be here and to share some of my thoughts and maybe to learn something from Patrick and Cyprian as well.
Well, I mean, as a professor, you're in the right place at the right time. Quantum's exploding. There's so much buzz right now about things getting real. And you guys are heavily involved, especially on the photonics side, which I just don't see a future where photonics doesn't play a role. Other modalities are interesting, and I'm sure they're going to play a role. But photonics seems the only way we're going to connect this stuff together.
You know what, Patrick? So I feel very pleased and honored to have heard what you said, because this has been what I have been trying to tell everybody, that since over 15 years ago, that hey guys, look at photonics, and photonics is inherently quantum mechanical. Of course, there are some technology and engineering challenges to implement quantum tech in photonics platform. But over the past 10 years, and we have seen lots of progress on both fronts. And now I think the opportunity for photonics to make big buzz and to have a strong push on the quantum technology transfer to industry right here. So I'm actually excited by the progress that we have been making at QCI, and the progress that people are making in all different areas of photonics for quantum.
Mm.
The other thing that Patrick and I were discussing a lot and were mentioning a lot, photonics also seems to be the one and only bridge between quantum computing and quantum communications, which is probably kind of like the cornerstone of the future of the field, right? So I think that's another very important angle when we talk about photonics.
This is 100% correct. So the only way to connect quantum computers over distance is by photonics. And we have seen in the digital era that we have been in over the since the late 90s, that so the power of computing is really multiplied when you can connect many computers together. And I have no reason to believe that this is not true for quantum. In fact, so I believe that the quantum future really hands on the success of quantum internet as well, where we connect many quantum devices by internet. And the only way to do it, to the best of my knowledge as a physics professor, is by photonics. So this is why precisely as you just said, that well, since we are going to use photonics, to connect quantum machines, quantum computers, the easiest way to make it happen is to use photonics to build quantum machines, to build quantum computers, so that you don't need to have this intermediate step of converting the information carrier of, say, from the atom to photonics or vice versa. But on the other hand, so I'm not saying that we have to use photonics to build quantum computers. In fact, so I believe in the opposite. I believe that the quantum space is open not just in the technology approach, but also in this wide application space. I believe the future of quantum will consist of, say, those atom-based, superconductor-based, ion-based, and photonic-based quantum computers, and each of them will take care of some niche applications in its own areas where it makes most sense in terms of the cost of operation, in terms of the speed to solution, for example.
We've said that. We've discussed the fact that there's no winning modality, that there's
Right.
so many modalities, and we may have others to discover that we haven't seen. It seems like any binary property at the quantum level can be turned into a qubit if you engineer it right.
Indeed. Precisely. Patrick, did you have a physics PhD?
I do not. No, but I hang out with people like you way too often, so it rubs off.
Impressed. Yes, indeed. So, in fact, any discrete quantum state system can potentially turn into information processing machine. And depending on what applications, it could be computer, right? It could be encoder, right? It could be sensor.
Amazing. I do have one question that might veer on to the professor side versus the CEO side of your personality, which is we've seen some articles in the past that said there was a hypothesis that maybe instead of entangling, instead of measuring and entangling, that you might take, especially in photonics, entangle millions of photons and measure along the way. So as a way to basically, because it's the fragility of the state that's our biggest challenge.
Yes.
And so like normally you take and you operate and then you entangle and then you measure. But someone posited, and I didn't really get enough about the article. I didn't read the underlying paper, that maybe you could entangle a huge amount of photons at creation and have like this herd of them that you could measure some of them along the way to make sure you're going the right direction. Is that something that QCI is looking at, or are you more the old-fashioned way of like manipulating entangled states as you go?
Let me answer your question.
And if that's an unfair question, I'm happy to move
No,
on because
it
it's a
is
weird question.
No, it is a very good and a deep question. So I can tell you this. Many physicists, including myself, have spent over 10 years in trying to find a way to efficiently create entangled two photons, just two. And it's already very hard. And the big issue there is the standard way for us to create entanglement. So the process itself is random, is stochastic, meaning that so you don't have much control of when the two entangled photons can be created. But say maybe on average, each time you try, you can say have say 8%, 5% probability of getting a entangled payout. This is actually an issue for using the photonics for quantum computing because just as you said, Patrick, for many applications, you do need to prepare many photons that are entangled. And now, if you only have 5 or 8% probability of to create one pair, so the probability of being able to get many pair would be very slim. So we don't like that. And I actually myself spent, starting from 2010. So really looked into the fundamental physics first and the engineering aspect of how to make it happen. So in fact, if we find a way to make it happen, although right now, so there's still some engineering challenge actually on the manufacturing side to make the device. But hey, so we find a way to allow you to deterministically create entangled photons so that when you say that, give me one pair of entangled photons, you will get one pair.
Yeah, we assume that's a step that everybody simplifies. Since the first time Cyprian and I started talking was, well, you entangle a couple of things and we skip that. And so it's fascinating how in depth it is and how hard we don't take it. We take it for granted that it's not as hard.
And so now, so this is actually what's happening now at QCI now. For that to happen, for the deterministic generation of entangled photons, you will need to make very specific photonic integrated circuits with some crazy parameters for you to hit. And so since I proposed this approach, say I think there are a total of 8 pretty crazy parameters for us to hit, and we have hit 7.
Wow.
We are trying to hit the 8th one in the QCI fab now. So I tell you what, so I feel good about it. But after have pushed this like for over 10 years, I'm kind of getting old. So I'm pushing my engineers that, okay, guys, I told you the recipe, right? You guys just make it happen, and they come back. Oh,
I'll be on the beach. Just let me know when it's done.
So the real requirement is that so you will have to make this a very high quality, what we call micro ring optical cavity, and in order to get the Q factor of the cavity. Okay, guys, stop me if I started to talk too much into physics.
No, that's fine. We like that.
we needed to cut some micron size bridge reach waveguide on a thin film lithium niobate wafer with the surface roughness like less than 300 picometer.
Wow.
So it is crazy, right? But I can tell you that that's what we have achieved last year. But this is just the first step, and there are multiple steps, and the team's working hard on that. While I probably can find one or 2 days to go to the beach, as Patrick listed. But now getting back to your original question, Patrick, because you really asked a astronomical question that can we entangle 1 million photons? I guess then after my long answer, the short answer is that yes, in principle, but I don't
Not
see
yet.
how in my lifetime. But fortunately, we don't need that. We don't need it to entangle 1 million photons for us to build a quantum computer using photonics. As long as, say, we can make hundreds of thousands of pairs of entangled photons, where 2 photons are entangled in each pair. So we can already build some very useful and very powerful quantum computers.
That makes perfect sense, because I think the context of the Entangle a Million was the fact that there was so much loss in transmission. But you're talking about calculation as well. You're talking about gates.
Yeah.
And so you guys have built a universal quantum computer gate-based with photonics.
No. So we have worked on this and we figured out how to build. So that this work is still ongoing. What we have
Okay.
now on shelf for customers to buy as of now is a specialized quantum optimization machine that
Okay.
definitely utilize quantum effects, but it is not gate based,
Okay.
and they are very good for solving a pretty large portfolio of optimization problems. But it is
Okay.
not a general purpose quantum computers.
Is that a goal down the line for you guys, or is that not an area that you're going into?
We are working on building the gate-based quantum computers. Yes, so this is our goal. But the approach that we are taking at QCI is that so we don't want it to define what kind of quantum computers or what quantum computers should look like by ourselves. In fact, so we go to the customers, we talk with them, and we understand what they really need. And
Okay.
then we build quantum machines to meet their need. In fact, very interestingly, so while physicists, including myself, were very fascinated on building the gate-based general purpose quantum computers, actually. So many customers, the feedback that we got from them uh, um, um, has been that so do you have a quantum machine that can solve my problems now? And what we find is that so for many of those problems, gate-based machine actually does not give us the edge, does not give us the advantage. Instead, some special purposed machines can solve their problems. So this is how we get started with the quantum optimization machine.
Cool.
I think that's very interesting, because one of the themes that occurs quite a lot, and we discuss about it quite a lot, is the difficulty in essentially embedding real world problems into the space of quantum, right? Defining a problem in a way that can actually be addressed, right? With a quantum device or a quantum computer, or however we want to name it. And I think besides the specific task of building these devices, the theoretical problem of defining the problem in a way that's suitable, I think is kind of the other big goal here for everyone in the field.
And do you know the fundamental reason for such difficulty for people in it to formulate the problem to run on quantum computers?
What is it?
This is because in many cases, say quantum computers have been designed based on the understanding of scientists, physicists, right? So it is that okay. So for example, just to use this gate based. So in fact, so there is no rule set that so we have to use the gate based. It was that okay. So when we open a classical computer, right? So you will have the memory, right? You have the processor, and there's a lot of transistors, right? So the easiest way to picture what a future quantum computer would look like is that okay, how about just we replace all the parts of a classical computer with a quantum equivalent, and to
It's what we know.
yes, if you wanted to build a new technology or build a new type of hardware by harnessing a totally different physics, right? So your starting point should not be try to box the new physics into an old architecture. You should go deep into the new physics itself, okay, and then try to find the most logical way to build the hardware according to the physics itself. And
this is why in every sci-fi movie, all the aliens look like humans. They just have different like nose ridges and things like that. It's the lack of imagination is what you're getting at.
Yes, and actually, so actually, so I have been. I mean, I had been struggled in the same puzzle, and but then since about 10 years ago, I started to tell myself that okay, let's really try to let quantum be quantum and try to make friends with quantum instead of try to box the quantum in a classical architecture. So let's build a quantum machine that observe the unique property of quantum physics itself, and
then see how we can leverage it.
How can we leverage it? So this is why we are building some quantum machines at QCI that is very different from what anybody has done. But hey, so it works, and we have found that so they can indeed solve problems very efficiently and give us better solutions. And in fact, so when we first announced this machine, many people said, "Oh, this is not a quantum computer," because in people's mind, it is that for a quantum computer, you have to have the gate base, you have to have the quantum memory, and we are doing something very different. But my definition of a quantum computer is that a machine that utilizes the quantum effects to solve problems with advantage that is unmatched by any classical.
And that's working for you because you guys just announced an AI Edge product, I believe, didn't you?
Yes, this is another pretty exciting development. In fact, so we know that AI is here to change the world. for good or for bad. I don't want it to.
It's like the internet. It's going to change things, but it's up
I
to us
think
how
the
it
jury's
changes.
still out on that one.
Right. And now, but one thing that we know for sure is that AI is going to consume more and more electric power, and it's not a sustainable mode to further develop the AI architecture by building nuclear power plants next to data centers. I don't like that idea, and I don't think that idea can carry us much further. So instead, so at QCI, we're asking ourselves, can we offload some complex and power consumption intense calculations from the digital to the analog optical domain? Because the moment that we can do that, we can, for example, reduce the power consumption per calculation by many orders of magnitude. In fact,
Oh, wow.
we have done some research in the lab, and we find that we can use a single photon for machine learning task, and a single photon has energy of 10 to the negative 19 joules. So just to put this in the context, Patrick, so the light bulb in your room now is probably emitting, if you're having it on, it's probably emitting like 10 to the 22, yes, 10 to the 21 photons per second. So
Yeah.
we just need almost no energy to perform that particular AI. So now this is why at QCI we are looking at photonics approach, and by incorporating photonics neural network layer with the digital layer, so that we can have this hybrid machine architecture that can reduce the energy consumption by 10 times, 100 times.
That's amazing. I mean, that's so much bigger than what we've seen in other things. So I don't know if you saw this in the news a while back, but Google came out with a way to compress memory usage by the leading models in training by 6-fold. This is a much bigger savings. And so that kind of thing, I think it was called TurboQuant or something on that name from Google that came out, memory management. And it changed the metrics of the cost, the data centers they were going to build. So this kind of thing could also have a big impact. Yep. It's something you just announced in the last month, I believe, right?
Yeah. So our first commercial product was released and last month, and it's called NeuraWave. And what it does is that so inside the box, so it is a hybrid neural network that precisely does what I said. So a part of the calculation is still done in digital, so on FPGA, and a part of that is done in the optics. And by combining the two, actually, so we have already seen significant savings in the power consumption. But this is just a start.
Yes. Well, and machine learning underlies everything. I learned that from Cyprian, right? If it weren't for the machine learning, we wouldn't be where we are in the LLMs, right?
No, but I think this comes at the perfect moment, because what we're seeing there is the end of the free tokens for everybody party. I think people are starting to realize that these huge models that are being used out there, right, are like huge energy consumers,
Mm.
and moving even kind of forward with these, it's just going to be not sustainable.
Mhm.
I think a few months ago, or even perhaps a year, there were a few very interesting papers that were published that were using the laws of thermodynamics
Mhm.
to prove that there is not enough energy on this planet to achieve like the Skynet level of artificial intelligence, because the curve is just exponentially increasing. So I think the timing of your announcement is just great, because people are starting to realize that the party's over, and especially the energy party is over, and there is like no unlimited possibility of moving forward with what we have, unless companies like you come with these amazing innovations where we literally kind
Scale
of
it back
cut
down.
orders of magnitude the energy consumption.
Yeah.
That's the, like, to quote a famous movie, this is the way.
Yeah.
Thank you so much. I think yes, and we are we are striving to contribute, but say I'm glad to say that there are other players, so they are making the effort along the same lines. So I'm actually pretty optimistic that uh, for photonics will play more and more important role in AI. So, even a couple of years ago, NVIDIA is really looking at photonics to move the data from GPUs to GPU, right? But now
Hmm.
we should be looking at photonics not just for transferring information, but also for computing, processing the information. And I believe that there is a very bright and exciting future there. And one thing that I believe everybody will benefit from is that the tokens could become cheaper and cheaper as we adopt more and more photonics, because the energy consumption will drop down significantly as we integrate more and more photonics into
Hmm.
AI architecture.
And we have to say something before we stop, right? Which is critical. Photonics, and if we talk about in the context of energy, photonics has one like huge advantage, which is it operates at room temperature.
Yes.
Yes.
That's
Yeah. Well, so actually, this is not a very very interesting topic that if I may, I want to share some thoughts that I have had for a long time.
Please.
As a physics researcher, actually, so I feel that there's a major misconception that quantum can only happen at room temperature. So, in fact, if you open any quantum mechanics book, there's no such thing called cryogenic or cold or closed system. In fact, so we have seen so many signs that quantum effects do exist at room temperature. In fact, so quantum effects are already with us in many biological systems. So, and I'm not sure if you guys heard that actually. So, the photosynthesis process that happen now in any green plant. So there's quantum effects there. So
Mhm.
in fact, the quantum effects help uh, transporting the energy and to store at the bottom of the green leaves. Okay, so quantum effects already exist in nature at a room temperature in complex biological systems. We don't need to put the leaves in a cryogenic fridge. In fact, we'd better not do.
That's right.
So then the big question is that why do we need to go to cryogenic to build quantum computers? And so nature has already told us clearly that no, you don't need to do that. And so this is also a guiding philosophy at QCI. I've been telling everybody that, okay, guys, I know that it's easier for us to observe some quantum effects at cryogenic temperature, but we don't do it at QCI. Everything we do is room temperature. Why? Because we want every technology that we are innovating, engineering, and turning that to manufacturing will end in people's hands.
Right.
We don't want any of our users to buy the big cryogenic fridge in order to use QCI product. Instead,
Amen.
They should be able to buy our product and put in their backpack and just use it as another, say, computing device, communication device.
I really love the philosophy you have of like letting the physics guide how we use it, and not trying not to resort to cryogenics. I think we're out of time, but I really hope you'll come back and talk to us again. It's been a great conversation. Is there anything that you still want to mention before we wrap up?
I just want to say that I really appreciate for this opportunity to connect with you, and I hope that so my honest opinion actually so mainly as a physics professor, and can be perceived as a scientific and scientific insights instead of my comments as the CEO, because I really shared what I have been thinking and what my true belief is.
Yeah. I think we'd be all better off if all the CEOs were also physics professors.
I'm not sure about that.
Thanks again for joining us, and hopefully we'll see you again soon. Thanks again.
Bye.
Thank you very much. It's been a pleasure.
All right. Bye, everybody. See you next time.
Thank you. Thank you. Bye.
Bye.
Cybercrime is one of the biggest threats to businesses of all sizes and industries. With almost 500,000 open cyber positions, the problem is compounded by the lack of available talent in the marketplace. At Pulsar Security, our elite team of highly credentialed experts collaborate with you to assess your current defenses and develop solutions tailored to your specific needs. With services ranging from cybersecurity education to advanced penetration testing and red teaming, you can start reducing your risks today. Visit pulsarsecurity.com and let's secure your digital future together.